These slides are about the Gauss's law. Gauss's law, also known as Gauss's flux theorem, is a law relating the distribution of electric charge to the resulting electric field. The surface under consideration may be a closed one enclosing a volume, such as a spherical surface. In these slides, we describe a general relationship between the net flux through a closed surface, often called a Gaussian surface, and the charge enclosed by the surface, the relationship known as Gauss's law, and it has a fundamental importance in the study of electric field. Let us again consider a positive point charge q located at the center of a sphere of radius r. We know that the magnitude of the electric field everywhere on the surface of sphere is E equal to Ke q divided by r square. The field lines are directed radially outward and hence perpendicular to the surface at every point on the surface. That is, at each surface point, vector E is parallel to the vector del Ai, representing a local element of area delta Ai surrounding the surface point. Therefore, vector E dot delta vector Ai equal to E delta Ai, and we find that the net flux through the Gaussian surface is phi E equal to surface integral vector E dot d vector A, which is equal to surface integral E d A, and which is equal to E into surface integral d A, where we have moved E outside of the integral because by symmetry E is constant over the surface and given by E equal to Ke q divided by r square. Furthermore, because the surface is spherical, surface integral dA equal to A, which is equal to 4 pi r square. Hence the net flux through the Gaussian surface is phi E equal to Ke q divided by r square into 4 pi r square, which is equal to 4 pi Keq. Recalling that Ke equal to 1 divided by 4 pi epsilon naught, we can write this equation in the form phi E equal to q divided by epsilon naught. Note that the flux through the spherical surface is proportional to the charge inside. The flux is independent of the radius r because the area of the spherical surface is proportional to r square, whereas the electric flux is proportional to 1 divided by r square. Thus, in the product of area and electric field, the dependence on r cancels. Now consider several closed surfaces surrounding a charge q. As shown in figure, surface S1 is spherical but surface S2 and S3 are not. From equation, the flux that passes through S1 has the value q divided by epsilon naught. As we discussed in the previous slides, flux is proportional to the number of electric field lines passing through a surface. The construction shown in figure shows that the number of lines through S1 is equal to number of lines through the non-spherical surfaces S2 and S3. Therefore, we conclude that the net flux through any closed surface is independent of the shape of that surface. So the net flux through any closed surface surrounding a point charge q is given by q over epsilon naught. Now consider a point charge located outside a closed surface of arbitrary shape, as shown in figure. As you can see from this construction, any electric field lines that enters the surface leave the surface at another point. The number of electric field lines entering the surface equal the number leaving the surface. Therefore, we conclude that the net electric flux through a closed surface that surrounds no charge is zero. Consider the system of charges shown in figure. The surface S surrounds only one charge q1. Hence the net flux through S is q1 divided by epsilon naught. The flux through S due to charge q2 and q3 outside it is zero because each electric field lines that enters S at one point leave it at another. The surface S prime surrounds charges q2 and q3. Hence the net flux through it is q2 plus q3 over epsilon naught. Finally, the net flux through the surface S double prime is zero because there is no charge inside this surface. That is, all the electric field lines that enter S double prime at one point leave at another. Gauss's law, which is a generalization of what we have just described, states the net flux through any closed surfaces phi e equal to surface integral vector E dot d vector A equal to q in divided by epsilon naught, where q in represents the net charge inside the surface and vector E represents the electric field at any point on the surface.